We're going to look at two problems here that are going to involve velocity-dependent forces. What that means is that these are forces where the amount of force changes based on how fast something is moving, and because of how force is related to acceleration, it becomes a really complicated problem to solve when the amount of acceleration depends on how fast the object is moving, so that the rate of change of velocity is dependent on the actual velocity. Okay, so we're going to take a look here, and the first one we're going to say is there's a ball being dropped from rest, and we'll say that, so it's being dropped from rest. It's going to fall downward, and it's going to experience an upward force as it falls. So it's got its weight pushing downward, right? And it's got this upward force that is, we'll say it has a strength equal to BV, where B is some constant related to the properties of the ball, and V is how fast the object is going. And so what we're going to do here is we're going to look at a whole bunch of things. The first thing is we can actually figure out how fast this object is going when it stops accelerating, because the faster this gets, the stronger this force is, and the closer it comes to balancing out gravity. And so in that case, we would say that acceleration eventually will stop, in which case the mg down minus the bv up will equal 0. And so that mg would be equal to bv, or v would be equal to mg over b. And so this is called the terminal velocity, and this is when it stops accelerating. And so we've done all this stuff in class talking about things in free fall where there's no air resistance and things just continue to accelerate forever. Well, in reality, everything has some amount of air resistance, and so everything's going to reach a terminal velocity. Some things reach it faster and fall much more slowly. You could think of like a piece of paper, for example, falls really slowly, and that's because it has a really strong force of air resistance relative to its weight, and so we're going to have a really low terminal velocity, and it reaches it pretty quickly, whereas you have something that has a more efficient shape for falling, like a bowling ball, in which case it's going to fall much faster because the value of this relative to mg is going to be much smaller. Okay? And so we found our terminal velocity. The next step might be to say, well, I want to find a function for the velocity with respect to time. So I don't know, I want to know how fast it's going to be moving at any moment based on how long it's been falling for. We know it started from rest and it's going to increase in speed over the time. Well, if it was just g, we could use kinematics to figure it out, and we could even write a function for it, etc. We can't do that because it doesn't have a constant acceleration, and so we'll start though by writing a net force equation for that scenario. And so since it's not at terminal velocity, we'd say that the net force adds to be equal to ma. We're going to say down is positive because that's the direction of the velocity, and we're writing an equation for velocity, and so that's going to be equal to mg minus bv. Okay, so we've written this equation, and so let's say you're taking an AP test, and the first thing they might ask you to do from here, or the next thing would be to write a differential equation. Well, we do know that acceleration is the rate of change of velocity, so a is equal to dv dt. And so if I replace a with dv dt, I've now written a differential equation, we call this, for the velocity of this falling object. And now, so the first step, we wrote the differential equation here. The second step, if we were going to then be asked to solve it, the first thing we have to do to solve this differential equation is what we call separate the variables. So in this problem, we have two quantities. We have v and dv, which is the first quantity, and then we have dt, which is the second quantity. Now it might be helpful to divide m over to the other side, so we'll divide everything by m. We left with bv over m here, and so we have dv over dt equal to g minus bv over m. And so we're going to separate these variables, so we'll multiply dt up to the other side. So I'm going to bring it over to here, so we get dv equals g minus bv over m times dt. And so unfortunately we have to get this v over to the other side, but because that v is attached to all this other stuff, it has to come with it over to here. And so we're going to end up, we divide this over, we get dv over g minus bv over m equal to dt. And so now we have separated the variables. So step 1, we wrote a differential equation. Step 2, we did the separation of the variables. Step 3, you might be asked to solve the differential equation, which means we have to integrate it, okay? And so we integrate actually both sides. So we're going to integrate the first side with respect to v, so that's dv over g minus bv over m. And we're going to go from v naught, which in this case was 0, to v, because we're writing it as a function for v. On this side, we're going to integrate with respect to t, and so we're going to go from 0 to t. Now, this side's the easy part because the integral of dt, the integral of 1, is going to be t. Okay, so that side's done. Now this side, much more complicated. We have all this stuff going on here. So we're going to use the u substitution method, and so we're going to set u to be equal to g minus bv over m, and so du is going to be negative b over m, and we'll put the little tails on these u's so we can differentiate them from v, and negative b over mv, or dv, sorry. Now we're going to solve that for dv. So we say dv equals, we multiply the m over and divide the b, we get the negative, so negative m over b du, and we're going to substitute that in here, and so we get 1 over u du, and so the integral of 1 over u is ln of u, so we get ln of u times, and sorry, it was negative m over b, right? For the dv is this times that, so we put that in here. Okay, and so then we get ln u times negative m over b. I'll actually put that in the front, equal to t, and so we'll substitute back in the u, which is g minus bv over m, and we're going to evaluate this from 0 to v. So we get negative m over b times ln of g minus bv over m. We'll evaluate here for b, or for v, and we'll minus ln, put it all in parentheses, g minus b times 0 over m, and all of that equal to t. Okay? And so from here, all of this becomes just minus ln of g, and this all becomes the ln, so this is still here, g minus bv over m, and now we have just this big mess all equal to t, and so we'll multiply this over to the other side, and in addition we can combine these using the division rule for logarithms and subtraction. So because it's subtracted, it's going to be this divided by that, and so this goes over to here, so that's going to be negative b over m times t, whereas this is going to be here ln of g minus bv over m all over g. Okay, so we're getting there. From here we could say, okay, I want to simplify this further. The g's could divide out, and so then I'm at, if we take it up to here, we get ln of 1 minus bv over mg equal to negative b over mt. Next step here, we want to get rid of this ln, so we need to raise both sides as powers of e. So we get 1 minus bv over mg equals e to the negative b over mt. And so we're getting close. We're going to subtract 1 from both sides. So we get negative b over mg times v equal to e to the negative b over mt minus 1. We'll multiply, let's do divide the negative 1, so b over mg times v equal to 1 minus e to the negative bm, or sorry, b over m times t. Alright, and then finally we'll divide everything by this, and we get v equal to mg over b times 1 minus e to the negative b over m times t. Okay? And so here now we have finally written our equation for the velocity of this object with respect to time. Now some things you can notice. We decided earlier that terminal velocity was equal to the mg over b, which is this right here. That's terminal velocity, that little piece right here. Okay, so this represents vt, the terminal velocity. And so if we look at this equation, well, when t is equal to 0, this term right here turns into 1, and 1 minus 1 is 0. So at 0 time, all of this is 0, and 0 times this is 0, and so we end up with a velocity of 0. But as time increases, this term here will approach 0, which means that we approach this value because it's 1 times that. So we approach this as our terminal velocity. Okay, so we approach that terminal velocity. So if we were going to graph this, the velocity of this over time, it would be something like this. We start from 0, and we have an asymptote right here that is at terminal velocity, which is the mg over b, right? Was the value of the terminal velocity. Okay, and so this is a graph velocity time. You might have on the AP test a situation where you have to make a graph for this differential equation. In this case, this is what our velocity looks like. It's speeding up, it's approaching 0 because our acceleration, or it's approaching, sorry, not 0, it's approaching this terminal velocity because our acceleration is approaching 0. Okay, that's part 1. Now part 2 might ask us to actually go ahead and find the acceleration of this object with respect to time. So we found a function for the acceleration, or an equation here with respect to velocity, but we actually would need to take the derivative of this if we want to find it with respect to time. And then we could also graph it from there. So we're going to take that next step. Okay, so now we want to go ahead and do that. So we're going to take this equation here, and we're going to differentiate it with respect to t. So I'm actually going to first distribute this mg over b just to make it easier on myself. So I'm going to say v equals mg over b minus mg over b times e to the negative b over m t. So when we take the derivative, this term is going to disappear because there's no variable there. So we're going to take the derivative, find dv dt, and so we get this part goes away, so 0, and then we're going to, derivative of e is itself, so e to the negative b over m t, but we use the chain rule, so we're going to multiply by negative b over m. So we get negative b over m times negative mg over b, and we find that these m's cancel out, these b's cancel out, and the negative become a positive, and so we get that dv dt is equal to g times e to the negative b over m times t. And so what we can gain from this by looking at this carefully is a couple things. First of all, when the value of t is 0, then this value is 1, which means that we start with an acceleration equal to g when the time is equal to 0. Okay, but as time increases, this value gets bigger, and because this is negative, this term here is going to get smaller, and so this value of g, this acceleration here, will decrease. Okay, and so eventually this is all going to approach 0. If we graph this, it's going to look something like this. So we have acceleration, this value here is g, and then over time it's going to approach 0. You could probably do a better job drawing it than that. And it's going to have an asymptote at 0. Not much better, but there should be an asymptote here at 0. Okay, and so there we have graph the acceleration. We see the maximum acceleration is g. It approaches 0 because of this term. And so we've done our first differential equation. So this is called a differential equation. I don't know if you guys do these in AP Calc or not, but if you were to continue pursuing your math career, you would have an entire class devoted to this. And if you were to become certain branches of engineering, you might do this as part of your job potentially. But anyway, you can see that this is a little bit trickier than just a situation where you have constant forces, and this is actually why we've waited until this point to get into it. Okay, but we've got the basics here, and so the keys are writing a differential equation, separating the variables, and then solving it. And then if we want to get the acceleration, we have to then take the derivative, and then we've got these really neat graphs. And so all of these things could come up on an AP problem that involved a differential equation.